Okay, you can pick up this quiz during the break. I mean, it's over here. Now the answer is the angular velocities are all equal. But since the linear velocity is equal to the angular velocity times the distance from the rotation axis, the further away point has a larger speed. So the VC is larger than VB, larger than VA. Now, any questions you have before we continue? Okay, rolling without slipping, we will repeat them. Let's do a similar example. We will study the yo-yo. Yo-yo is basically rolling without slipping in an incline that is 90 degrees. Other questions? Okay, parallel axis theorem. The yo-yo. Other questions? Other things that are not so clear? Okay, so let's start with the parallel axis theorem. Now, one of the complications that we are studying now is rolling with rotation. Rolling with translational motion. We are just trying to combine both of them. If you have realized, we first started rolling around the fixed axis. Well, that is kind of a limited kind of motion. And now we are looking at the more general motion when our object both rolls and at the same time it's making some translational motion. Now, one complication is that, if you remember, we always first start by describing the motion. How do we describe the rotational motion? If we didn't allow our axis of rotation to move, then the description was kind of simple. We have a single axis that is fixed, and the object has some angular velocity. It might have some angular acceleration around that axis. But when we allow the axis to move also, there's an infinitely many choices of possible axes that we can use to describe the motion. Now, one way to do this is if, for example, let's imagine we have this object. Okay, we have, let's say, such an object that is rolling. And it also has some translational velocity. Now we can describe this motion as, let's say, it is rolling around this axis, and that axis itself is just making some translational motion. And another possible description is we can just take this other axis. It is rolling around this second axis, and that axis is translating. So both descriptions are valid descriptions. Then there is a problem though. When we were discussing rotation around a fixed axis, there was this moment of inertia that we calculated which kind of played the role of mass. So there is this moment of inertia which we defined as MI/RI squared or DI squared. MI being the small masses making my system, DI being their distance from the rotation axis, and this played in the similar role to the mass. This is what resists angular acceleration, just like mass resists linear acceleration, this resists angular acceleration. Now, if we fix this axis, let's say, in that case, we have a moment of inertia for rotations around this axis, but we also said that we can equally well describe the same motion, the same object, as if it is rotating around this axis. And for rotations around this axis, we have a different moment of inertia. Well, it is the same motion. So somehow, these two moments of inertia have to be related with each other. And that relation is given by the central axis theorem, which states that the moment of inertia through an axis passing through, let's say, the point A, it can be an arbitrary point, arbitrary axis. this is equal to the moment of inertia around the center of mass plus the total mass of the object times d squared, where m, total mass of the object, d, distance of the axis, a to the axis, passing through the center of mass. If you take this example, this is the axis that passes through the center of mass. I can describe exactly the same motion as if my ball is rotating around an axis, let's say, shifted over here, and that point itself is also making some circular motion. So that axis has some linear velocity, and my ball is rotating around that axis. Both these two descriptions are valid. It's up to you. You are free to choose whichever one you want. But you are not, for example, free to describe this motion as a motion around this axis. The direction of the axis should be the same in all cases. So that's why it is the parallel axis theorem. So instead of describing the motion as if it is rotating around this axis, you describe it as a rotation around the parallel axis. And this is the relation, this one. Now the proof, if you want, you can go over, but if you want, you can just keep this one in mind, this relation. Now, any questions on this parallel axis theorem? So basically, this allows you to calculate the moment of inertia for a given motion only once. You calculate it once, and so whichever description you want to choose, whichever axis you want to choose, you use the same moment of inertia. You just modified it through this relation. The proof? Well, I will just go back. It's just putting in the definitions. Now, this is the end of the parallel axis theorem. Okay, there's also this perpendicular axis theorem. This last line. Well, now the perpendicular axis theorem was related with objects like this, or wheels, in the sense that it is very thin. There is no z coordinate, so you can assume that you put this on the xy plane. So none of the points on this object has any significant z component. So that all the z coordinates of all the points on my object, they are made more or less zero, approximately zero. So what we do is we just use the definition of the moment of inertia for rotations around the z-axis, let's say this axis. This is how we define it. This is the distance squared of any point on my object from the z-axis. Now we can just split it into two. And now if you take, let's say this is the z-axis now. This is the z-axis, let's say this is the x-axis, this is the y-axis. If you take this point, the distance of this point from the x-axis is nothing but its y-coordinate. So again, if you just look at here, if you take this point, the distance of this point from the y-axis is its x-coordinate. So if you look at this expression is nothing but the mass of that point multiplied by its distance from the y-axis squared. But this is nothing but the moment of inertia for rotations around the y-axis. And this is nothing but the moment of inertia for rotations around the x-axis. So this is kind of the proof. Now, of course, the distance from the y-axis, the exact form would have xi squared plus zi squared. The exact definition of ix or I1. xi squared plus zi squared. This is the exact expression. But we know that zi is almost zero. So this is approximately true. This perpendicular axis theorem for a real physical object is approximately true, but this parallel axis theorem is exactly true for any object. Other questions? Okay, let's look at the yo-yo. Have you ever played with yo-yo? How many of you played with a yo-yo? Okay, so you already know what it is. It's, by the way, it's also a flywheel. You can call it a flywheel. So what it does is you have this circular object, you wrap some string around it, so you just let it go. And what happens if it will unwind the string, let's say it's rolling down, and when it reaches down, it still has kinetic energy of rotation, so it will keep rotating. And it will keep rotating, and it will just keep rotating, and it will just move up. So here it's moving down, it will just go down, and then it will start to roll. It will continue rolling, and it will just go up. This is what the yo-yo is. Now let's calculate its acceleration. What's the acceleration of a yo-yo? Now let's see, at this instant, I'm just looking at this instant. What is the velocity of this point? It is zero. The string is not elastic, so at that point is just a choice, it cannot move. So we can just as we can describe this motion as rolling around this point, around the center of mass, where the center of mass is being translated, or we can also say that at this instant my object is rotating around this fixed axis. Now let's say that the moment of inertia of the yo-yo around an axis passing through the center of mass is I center of mass. And in that case, if we call this point A, the moment of inertia around the axis passing through the A. So at this instant it is rotating around that point. IA is equal to the moment of inertia around the center of mass plus m times r squared. This is the parallel axis theorem. So I know the moment of inertia through an axis passing through the center of mass, but now I'm describing the motion as a rotation around this point, not around an axis passing through the center of mass. So I just parallelly shift the moment of inertia, so this is my new moment of inertia. What are the forces acting on my yo-yo? There is the weight, the force due to the weight. And there's also the tension, the force due to the tension. There are these two forces. Now let's calculate the torque acting on my object. Let's say this is my z-axis. What is the torque? I have two forces that will be creating the torque. What is the torque created by the tension around the point A? The tension doesn't create any torque around the point A. So it is zero. What about the torque created by the weight of the object? R times mg. What is the direction of this torque? Towards you? Yes. So it's in the z direction. So now we know the torque around A. Then we can calculate the angular acceleration around A. The angular acceleration, remember the moment of inertia around the point around the axis point going through A times the angular acceleration around the axis going through A. This is equal to the torque, which is mg times r. This is what we had derived. Or alpha is equal to mg times r over Ia. So this is the acceleration, angular acceleration around this point. Now we can calculate the linear acceleration of this point. Because remember, the tangential acceleration was always equal to alpha times r. Alpha times d. Again, d being the distance from the rotation axis. So this is equal to the tangential acceleration of the center of mass would be mg over Ia times r. Well, the distance is also r, so this is the tangential acceleration of the center of mass. So the tangential acceleration of the center of mass, this is equal to mr squared divided by r, the moment of inertia around A times g, or mr squared over the moment of inertia around the center of mass plus m times r squared. G, center of mass, is equal to 1 over 1 plus I center of mass over mr squared times g, which is always less than g. So now we know the acceleration of the center of mass. What about the tension on the string? How can we calculate the tension on the string, now that we know the acceleration of the center of mass? Newton's second law, how do we use it? The net force is always equal to the mass times the acceleration of the center of mass. This is always true whether the object is rotating, translating, or whatever weird motion it can be doing. This should be always true. Now we know the acceleration of the center of mass, so we know what the total force is. Its magnitude is equal to mg divided by 1 plus I center of mass divided by mr squared. This should be the total force, total downward force. But this, we already know that this is mg in the downward direction minus the tension. So we can just determine the tension. Tension is equal to mg, I center of mass over mr squared divided by 1 plus I center of mass over mr squared, or mg, I center of mass divided by I center of mass plus mr squared. Now, any questions? Now let's look at one more thing. Let's look at tension times R. This is equal to mg, or let's look at tension times R divided by I center of mass. This is mr divided by I center of mass plus mr squared times g. Well, we had already determined the angular acceleration. Angular acceleration is mr squared over I center of mass plus mr squared times g. Now here. This was the angular acceleration that we had already determined. Now if you look at it over here, this is exactly equal to the angular acceleration. This is equal to alpha. Or we can just rewrite this. Tension times r is equal to I center of mass times r, times alpha. Again, let me redraw it. This is the tension, this is the weight, this is r. Now what can you say about tension times r? It is the torque around the center of mass. Now if we try to write the torque around the center of mass, the weight does not contribute. It's only this tension that contributes. So we have the total torque around the center of mass is just T times R. And this is equal to I center of mass times alpha. Now this is not the theorem that we proved before. Remember, before we proved that torque is equal to I times alpha. But torque is equal to I times alpha. And this R proof only shows that torque is equal to I times alpha only for rotations around the fixed axis. At least in this special case, we see that it is also true for the rotation around the center of mass. Okay, there are two main differences here. One is the center of mass is moving. The axis going through the center of mass is in motion. Well, if it was moving at constant speed, then we could easily go to a reference frame in which it was at rest, and we could calculate everything in that reference frame and just claim that this is true. But center of mass is even accelerating, so even if you go to a reference frame which is moving with the center of mass, that is not an inertial reference frame, so in general we cannot use this theorem. But it just turns out that torque is equal to I alpha. Torque is equal to I times alpha. This is valid in two cases. If one rotation axis is fixed. Or moving at constant velocity. And two rotation axis goes through the center of mass. In these two cases, we can still use this relation between the torque and the angular acceleration. Now, of course, in these two cases, the torque will be different. Just as you see in the yo-yo example, if you write down the torque through the axis that is instantaneously at rest, it is the weight that is creating the torque. If you write the torque around an axis passing through the center of mass, in that case, it is the tension that is creating the torque. So the expression for the torque might be different. The moment of inertia will be different. You can use the parallel axis theorem to relate these two moments of inertia. But the relationship will still hold. It will be still valid. Which one? In the first case, the rotation axis has zero translational motion. So it is this motion. The axis is not being translated. In the yo-yo example. In this yo-yo example, we are saying that the yo-yo is at this instant, it is rotating around this fixed axis. At the next instant, of course, this axis will not be there. But at this instant, this rotation axis is at rest. It's not moving. It's just like the rolling example. Sorry? Well, let's see. Let's look at this point. And let's look at this point. What can you say about the accelerations of those 2 points at this instant? I would not say they are the same. To say at least one thing, this point is moving towards the left, is accelerating towards the left. This point is moving towards the right, and it will stop there when it reaches that point. So it's also this point probably has some acceleration towards the left. But when you reach this point, that point has zero acceleration. Has zero velocity, zero acceleration. Not happy with that? Okay, it will make a nice homework. Other questions?
So, is the only acceleration the weight of gravity?
Of the yo-yo? No, you say the acceleration of the center of mass is always and always determined by the total force acting on my system. The total force, the net force. Now, if you look at the yo-yo, there are two forces acting on it. There is the weight and there is the tension acting on the yo-yo. So these two forces determine the acceleration of the center of mass, not only the weight.
If we use the y and x coordinates, only the y component of, y direction, the acceleration.
I mean, yeah. There is no horizontal force, so we say that the only force is vertical. Well, in real life, I don't think you will be able to keep the yo-yo so straight. But approximately it will be almost straight. Now let's look at one more example. Rolling with sloping. Now in this problem, what we will assume is this one. We have the ball. We started spinning in some direction, and we just let it on the ground. Initially, it has zero translational velocity. The center of mass has zero translational velocity, but definitely it has some rotational speed, the surface at least. So the bottom surface is moving in this direction, whereas the ground is not moving. So these two surfaces have some relative, non-zero relative motion. That is what we call the slipping. They will be slipping. It lasts for a very short time if you try this. Almost instantaneously it starts to move forward. So if for a very small amount of time, there will be slipping, and hence there will be some kinetic friction. The kinetic friction, the direction of the kinetic friction will be in that direction, because that is the only force that causes the acceleration of the ball. So it's accelerating in that direction, and after some time, it stops slipping and it makes rolling without slipping. So let's see how long it takes, or until it starts rolling without slipping. It is slipping now. It will start accelerating. As it accelerates, it slips less and less. And after some time, it will just start rolling without slipping. How long it travels before it starts rolling without slipping? So let's say this is the initial motion. So we have angular velocity that is very discrete. Omega initial is non-zero. Initial speed is 0. Those are the initial conditions we have. What are the forces acting on my system? Okay. What is the direction? To the right. This is the friction force. Is it static or kinetic? Your second chance. Is there a relative motion between the surfaces at this instant? It is not moving, but it's rotating. So if there is a relative motion between the surfaces, then it is kinetic friction. So this is kinetic friction. Other forces? There is a normal force. There is the weight. And that's it. By the way, this is not a free body diagram. If I wanted to draw the free body diagram for this object, this is what I would draw. It looks almost the same, but there is no ground in it. This is the free body diagram. Now let's stick with this one. What is the acceleration of the center of mass? Or let's write the total force first of all. Let's say this is x, y, and the z-axis is pointing towards you. The total force acting on my system, well, there is a friction force, which is mu k times n in the x direction. I know it's kinetic friction, so it's mu k times n. Plus the normal force in the y direction, plus its weight mg in the minus y direction. This is the total force. And I know that the object should be accelerated in the x direction. So this should be equal to m times a in the x direction. At this moment, I still don't know what the normal force is. So I cannot write that the kinetic force is mu k times mg. I don't know that yet. Now I need to solve this equation. Now when I'm solving this equation, I see that there is no y component on the right hand side. So it tells me that the y component should also be 0 on the left hand side. So n minus mg is equal to 0. Now I know that the normal force is equal to mg. Then mass times the acceleration. This is the x component of the total force on the right hand side. So on the left hand side, the x component is mu k times n, mu k times mg. So I can just cancel the m's, so I know that the acceleration is mu k times g. So this is the acceleration of the center of mass. And I know what the velocity of the center of mass, the speed of the center of mass is as a function of time. Or the velocity, the initial velocity was 0, so it is just a times t. It's motion with constant acceleration, v times t. This is equal to mu k g t in the x direction. So now I know the velocity of my object is a function of time. Of course, now there is a problem of the rolling. So what is the angular acceleration of this object? Now to determine the angular acceleration of the object, I need to calculate the torque divided by the moment of inertia around some axis. Now in this problem there is no axis that is fixed. There is no obvious axis that is fixed, so all the axes are moving, they are translating, etc. So the best choice would be to consider it as translation of the center of mass plus rotations around the center of mass. So I can just say that the acceleration would be equal to the torque around the center of mass divided by the moment of inertia around the center of mass. Now there are three forces here: the weight, the normal force, and the friction force. What is the torque created by the weight around the center of mass? Well, the weight just acts at the center of mass, so the torque will be 0. What about the force due to the normal force? Remember the torque definition. If you remember the definition of the torque, it is R cross F. For a given force F, R is the vector pointing from the axis toward the point at which the F is acting. So if you want to calculate the torque created by the normal force is not acting on the center, at the center of mass, so this R is non-zero, F is non-zero. But you see, this is R. We are calculating the moment of inertia, the torque, not the moment of inertia, we are calculating the torque around the center of mass. So the position of the point at which the normal force acts is at this point, whereas the normal force is at this direction. The angle between the two, 180 degrees. Now the definition, the magnitude of the torque is proportional to the sine of the angle between these two things. Well, sine of 180 is 0. So the magnitude of the torque created by the normal force is 0. So the normal force also doesn't create any torque. The only force that creates a torque is the friction force. What is the magnitude of that torque? It's the radius is at the magnitude of the torque. Let me write the magnitude of the torque also. This is R F times sine of the angle between the two. Well, the friction force is acting at this point. So it is distance from the center of mass, from the axis going through the center of mass, is the radius of this sphere, R. Now the magnitude of the friction force we had already calculated. This is the friction force is mu k times n. This is the magnitude, and n is mg. So the magnitude of the friction force is mu k times mg. The angle between these two the angle between the R and the friction force is 90 degrees. Sine of 90 degrees is just 1. What is the direction of this angular acceleration, of this torque? Let me write it this way. What is the direction of this torque? How we calculate the direction? This is R, this is R, this is F, R cross F. Just imagine this rotation. So it is in this direction, it's towards you. In the z-hat direction. This is the angular acceleration. Now we know the angular velocity as a function of time now. Omega 0 plus alpha times t. Now what is omega 0? The initial angular velocity. Well, we are given that its magnitude is omega e, its direction. We are told that it is into the screen, so it is in the minus z direction. Into the screen is the minus z direction. This is equal to omega I in the minus z direction. Oh, sorry, here we also have to divide by the moment of inertia. Plus mg mu k r over I center of mass in the z direction. So the angular velocity is mg mu k r over I center of mass times t minus omega I in the z direction. So we see that as time goes on, the angular velocity, it gets smaller and smaller. The magnitude of omega is omega I minus mg mu k r over I center of mass times t. This is the magnitude of the angular velocity. So I give it an initial angular velocity. So it slows down, the angular velocity slows down due to friction. At the same time, it gets faster, the center of mass gets faster due to friction. And after some time, it starts rolling without slipping. And we had said that when an object starts rolling without slipping, the velocity, the speed of the center of mass should be equal to the angular velocity times r. This is the condition for rolling without slipping. So let's see, we already know what the velocity of the center of mass is. Here, it's mu k gt, the speed of the center of mass. This should be equal to, well, we know what the magnitude of omega is. Times r. Let's say this is t0. This is t0 is the time at which the ball starts rolling without slipping. So this way, now after this time, neither this equation nor this equation will be valid. These two results, this one and this one, they are valid only until the ball starts rolling without slipping. Because once the ball starts rolling without slipping, in that case, the friction force over here is no longer kinetic friction. In fact, once it starts rolling without slipping, there won't be any friction force. So in an ideal case, when there is no drag force, when there is no rolling friction, etc., the ball will just roll until infinity after that time. With a constant angular velocity, with a constant linear velocity. Now, any questions? No, not even static friction. Let's see what happens if why should there be? Because you see, static friction arises arises only if you have two surfaces that try to slide on top of each other. If two surfaces are not trying to slide over each other, there's no static friction. So when you have this rolling without slipping, the surfaces, they do not try to slip on top of each other.
It's like they're naturally in the
Yeah. Now, even if at that moment they lose contact, you separate them. I mean, the corresponding points, they will just be, there won't be any relative motion. Other questions? Okay, see you after the break.